So north, south, north, south. Okay. Now there are more in number, less in number, right? And that's why if you see a net magnetic moment, okay, that will be in the direction of applied magnetic field, right? So whatever ML we are talking here, so this ML, this is the net magnetic moment, which is of course in the direction of applied magnetic field, right? I have a question now. Why we have M is equal to 0 when there was absence of magnetic field? Because in the absence of magnetic field, the nuclei are randomly oriented, right? And that's why one magnetic moment is going to cancel the other. And that's why the net magnetic moment is equal to 0, right? We apply the external magnetic field. These are like most of them lined up in the external magnetic field, very few in the rest, right? But as most of them are lined up now in the same direction as B0, we have a net magnetic moment here, and we call this as ML, which is nothing but the longitudinal magnetic component. Okay? Fine. So now you look at this diagram, that longitudinal magnetic component is in the direction of applied magnetic field. It is not possible to measure this ML, right? So now what we do is this. Yeah, I forgot one thing. Remember I said that they are spinning like this, okay? So we have a frequency of spinning, right? We call that as a Larmor frequency, and the Larmor frequency is given by zeta into B0. It's actually Garamagnetic ratio we call it as a, and B0 is the strength of applied magnetic field, okay? And if you talk about the F0 value, the standard F0 value is 42.58 megahertz per Tesla, okay? I increase the Tesla, the frequency is going to increase, okay? Remember this number, this is 42.58 megahertz per Tesla. We call it as a Larmor frequency. Larmor frequency is nothing but the frequency with which there is a precession there, okay? Fine. And one more important thing, as I said earlier, this longitudinal magnetic component is in the direction of applied magnetic field. It is not possible to measure that, so we need to do something there. What we do is this. Now what you do? We apply the external RF pulse. Remember the Larmor frequency that we talked about, okay? The frequency was 42.58 megahertz per Tesla. We apply the external RF pulse, radio frequency pulse, of the same frequency as F0, right? Now when we apply the RF pulse of same frequency as F0, then what happens is this. Look, before the RF we were at this stage. Most of them in the direction of B0, very few in the opposite. Now when you apply the RF pulse, two things happens. Now you, whatever the large number of magnetic moments are there in the direction of B0, some of them flip around because, remember this was a low energy state and this is a high energy state, right? Because of this RF pulse, this gets the energy, they flip around. And in the second diagram, the condition is the number in the low energy state is exactly same as the number in the high energy state. Where the extra energy has come from? It has come from the RF pulse, right? Okay. Now, this is the first stage. What extra addition that is there is, look at these magnetic moments. They are spinning like that. Now there is no resonance among them, right? Because one is here, one is here, one is here, and one is here, right? If you continue to apply the RF pulse, what happens is, this 4, like for example, this 4 will come into resonance. I hope you know resonance, right? So this 4 comes into resonance, this 4 comes into resonance, and this single structure and this single structure, it continues to precess now. Okay. So now the RF pulse has done two things for us. It has taken some of the magnetic moments from low energy to the high energy. Now we have equal number in low energy, equal number in high energy. The next thing that has done is, right now there was no resonance between the nuclei, but if you continue to apply the RF pulse, this precision will come into the resonance, right? Look at that figure, it is looking like a single straight line there. Getting what I'm saying, right? Okay. Now this continue to precess. Now if you talk about the net magnetic moment, right? What happens? Look at this line. So we have one line here and one line here. Okay. If you take the components of this vector, one component will be here, one component will be here, one component will be here and one component will be here. This one and this one in opposite direction, of course, going to cancel each other, and the net magnetic moment will be this direction, right? Now, if you remember the earlier figure, in the earlier figure, when the RF pulse was not there, the net magnetic moment was like this. When the RF pulse came, the net magnetic moment goes around like this, right? So we can say with the RF pulse, there is a 90-degree phase shift has happened in the net magnetic moment. Getting what I am saying, right? Now, in this diagram, ML was in the direction of magnetic field, was not possible to measure, but now the condition has changed. If you see the B0 direction, B0 is in this direction, but now the net magnetic moment is in this direction. And remember one thing, we have a circular fashion there, right? So it is not only like this, it is spinning around like this. Why it is spinning around? Because this structure is also spinning around, and that's why this magnetic moment will also spin around. Okay. Now what happens? Now we have some signal, because if we have this magnetic moment like this, we call it as MT. MT stands for the transverse magnetic moment. Earlier was the longitudinal magnetic moment. Now this is spinning around like this, right? You put a coil here, you put a coil here, right? Now the condition is the magnetic moment is spinning inside the coil, and of course, because of the spinning of magnetic moment inside the coil, we are going to have some current. Current is law, right? Okay. So in earlier case, where there was no RF pulse, we are not getting any current, not getting any voltage, not getting any signal from MRI. But now, once you apply the RF pulse, that MT is rotating in a coil, 90-degree phase shift to the B0, right? Now, as we are having a rotating magnetic field inside the coil, we have the current, we have the voltage, and we call that voltage and the current, and that is nothing but our MR signal. Getting what I am saying, right? Okay. So to get the MR signal, only the magnetic field is not sufficient. You require the RF pulse also. But remember, the RF pulse frequency should match the precision frequency of nuclei. Okay? If the precision frequency is 42, the RF pulse should be 42 to make it flip by 90 degrees. Getting what I am saying? Right? Okay. Now we have two conditions. One we call as a T2 relaxation and one is called as the T1 relaxation, right? Now what happens? We know this diagram. We talk about T2 relaxation now. So we know that diagram. That has happened because we applied the RF pulse, got the MT. MT is rotating, that's fine. But now let us say we have removed the RF pulse, right? So we are going back to the same thing again, right? You remove the RF pulse, what is going to happen? The first thing that is going to happen, can we say this is resonance now? Yes, that was resonance, right? You remove the RF pulse, the resonance will remove, right? You remember this diagram, right? Right? Earlier, you look at the middle one, there was no resonance. Then the resonance happened, right? Remove the RF pulse. The resonance, the resonance will remove, and you are going to go back to the second figure. Okay. So now we are going to go back to the second figure. The time in which this happens is called as the T2 relaxation, right? Resonance gone, and we have the equal number in low energy, equal number in high energy. This is called as the T2 relaxation. But now in the T2 relaxation, your MT is 0, right? And of course, when MT is 0, there is no MR signal, because MR signal is because of MT, because MT was rotating, right? As there is no resonance now, that's why MT is equal to 0, and there is no MR signal. What is T1 relaxation? Now, you start with the same figure, right? But remember, the original figure is not like that. Okay. In this figure, the number in low and the number in high are same, right? But naturally, the number in low is more compared to number in high, right? So the time in which this happens is called as a T1 relaxation, right? We can see from this figure, the number in low and the number in high are same. You wait for some time, don't apply any RF pulse. this will go back to the same situation again, right? So the number in low will be more compared to the number in high, right? And of course, with this diagram, we have a longitudinal magnetic field associated. Getting what I'm saying, right? So transition from this to this is T2. Transition from this to this is nothing but T1, right? Now there are different types of MR imaging. One we can call as a T1 weighted MR image, and one is called as a T2 weighted MR image. This happens if we play with T1 relaxation and T2 relaxation. We will be getting the T1 weighted image and the T2 weighted image. Okay, I'm going to explain. Not going to explain this.